Good morning, students. Today we are going to discuss a topic about the moment of inertia, and we'll discuss about what is moment of inertia, the definition of moment of inertia, and the relevance of moment of inertia, and the physical relevance of moment of inertia in the application of mechanics field. So, what is moment of inertia? Moment of inertia of an area is a purely mathematical term which will give you the quantitative estimation of the relative distribution of an area about some referral axis. So what does it mean? It means that if you have an area of A and there is an axis AB, so the moment of inertia is actually give you the relative distribution of this area about this referral axis. So if you have another area like CD, so this is another axis CD. So the relative distribution of the A about this CD and the relative distribution of the area about this AB will be different. So the moment of inertia of the area will be different from different axes. We are choosing different axes for getting different moment of inertia. So what is the relevance of moment of inertia? See, you know the definition of inertia, because what is inertia? Newton's first law gives you the definition of inertia. Inertia is the property of a body which will actually help the body to remain its uniform state of rest or uniform motion. So we know that if you have two different masses, one is a smaller mass, another one is a bigger mass, we need to produce the same linear acceleration for the two different masses. So for the higher mass body, we need to give more force to produce the same linear acceleration compared to the lower mass of the body. So in a similar way, we can say that actually the moment of inertia will give you the rotational inertia. So for the rotational motion of a body, we will use this term moment of inertia. That means if you have a higher mass and a lower mass, we need to produce the same angular acceleration of the body for the two different masses. We need more torque for the higher mass body to produce the same angular acceleration compared to the lower mass. Okay. And you know that the difference of the center of gravity and the centroid. So centroid and the center of gravity is analogous. For centroid is actually we are using that term for two-dimensional bodies, the 2D figures, and the center of gravity, the same concept we are using it for actually the body has got some mass. So in a similar way, moment of inertia is like two different types. One is area moment of inertia and the other one is mass moment of inertia. So what is area moment of inertia? When we are using the term or calculating the moment of inertia for an area, that is a two-dimensional figure, it is called area moment of inertia, or it is also called second moment of area. So second moment of area and area moment of inertia actually they are same. If you are calculating the moment of inertia for a body which has got some mass, then it is called the mass moment of inertia. Today we are going to discuss about the second moment of area or area moment of inertia, and we need to discuss about the mass moment of inertia the coming classes. Okay, now we are considering a body A and we have an axis AB. So the body, we are considering an elemental area dA at a distance r from the referral axis AB. We need to calculate the moment of inertia of this area about AB. So actually there is an equation for calculating the moment of inertia. This is sigma r square dA will give you the moment of inertia of this area about this axis AB. So this sigma r square dA is actually we are using when this area is composed by a small discrete area. We are assuming that the total area is built up by continuous masses or continuous figures. Then we can use the integration method, that is integral r square dA will give you the moment of inertia of this area about this axis. Okay. So why it is called the second moment of area? You can see that we know that r into dA is the first moment of area. That is, the dA is the area and r is the distance. So r into dA is the first moment of area and r square dA is the second moment of area. So the integral of the second moment of area is actually will give you the value of the moment of inertia. Okay, so I told you what is the practical relevance or physical relevance of the moment of inertia in the field of mechanics, because when you are calculating the moment of inertia of a body, it will give you some quantitative estimation. So fine. So if a body has a moment of inertia, okay, the unit of moment of inertia is, you can see that it is r square dA for an area moment of inertia. So r square dA, r is the unit in meter and r square, so it is meter square, and the area, you know, the unit is meter square. So total, actually the unit is m raised to 4. Using the meter raised to 4 or mm raised to 4 for our calculation for the area moment of inertia. And the mass moment of inertia, I will tell you later. Actually, the unit of mass moment of inertia is kilogram meter square. Okay, so today we are discussing about the area moment of inertia. So this is actually meters raised to 4 over mm raised to 4. Fine. Okay, so we need to define two terms like centroidal moment of inertia. What is centroidal moment of inertia? So IAB is the moment of inertia of this area about an axis AB. So you know that for a body there should be a centroid. Now imagine that G is the centroid of this area, and the axis, two axes passing through the centroid. This axis is parallel to the x-axis, so this is centroidal x-axis, and this axis is parallel to the y-axis, so this is centroidal y-axis. So the moment of inertia of this area about this axis is denoted is by Ig xx, and this one is Ig y. Okay, so this is actually centroidal moment of inertia. That means the moment of inertia of a body about the centroidal axis. Okay, now we need to study two theorems. One is called parallel axis theorem and the other one is perpendicular axis theorem. So the parallel axis theorem has some high relevance in our case compared to the perpendicular axis theorem, because we are solving most of the problem using our parallel axis theorem. So we need to derive and we need to define and derive the two theorems, parallel axis theorem and perpendicular axis theorem. I will derive the two theorems which you have probably studied these theorems in your +2. Anyway, I will derive the two theorems. We need to by heart these theorems, and you need to know how to derive these theorems. Okay, we need to define and derive the two theorems like perpendicular axis theorem and parallel axis theorem. So first we are going to derive the perpendicular axis theorem. And perpendicular axis theorem states that if Ixx and Iyy be the moment of inertia of two mutually perpendicular axes like xx and yy, and the moment of inertia of a third axis is zz, which is mutually perpendicular to the other two axes and which is passing through the point of intersection of the other two axes, then Izz will be equal to the sum of the moment of inertia of the other two axes, that is Izz equal to Ixx plus Iyy. So in this figure we have an area A and there is an elemental area TA. This is our y axis and this is our xx axis, and the z axis is actually, this is perpendicular, mutually perpendicular to the other two axes. So it would be look like this, and the figure is in the xy plane and we have a z direction, there is a zz axis which is mutually perpendicular to the other two axes, and the point of intersection of the three axes is O. Okay, so from the definition we can say that the R is the distance between the elemental area and the zz axis. So we can write Izz equal to integral r square d. Okay, from the figure you can see that the elemental area is at a distance x from the y-axis and y from the x-axis. So this one is a right angle triangle. So the r square equal to this hypotenuse, it is equal to x square plus y square. So we can rewrite the equation, that is r square equal to x square plus y square d. So separately this will become x square dA plus y square dA. So what is x square dA? X square dA means the relative distribution of this area about y axis. So x square dx is your I y and y square dA is your I xx. So finally we can rewrite the equation like I zz equal to I xx plus I yy. So this is the perpendicular axis theorem, which states that the moment of inertia, if you have two mutually perpendicular axes xx and yy, and the moment of inertia of the two axes is ixx and iyy respectively, then the moment of inertia of a third axis, which is mutually perpendicular to the other axis and which is passing through the point of intersection of the other two axes, then this is equal to ixx is equal to ixx plus and iyy. So this is the perpendicular axis theorem. If they are asking the proof and the definition, you should write the definition and derive this proof. Maybe it will ask for a 5-mark question. So secondly, we are considering the parallel axis theorem. So parallel axis theorem has a high relevance in our syllabus. So it is also called a transfer axis theorem. So I'll tell you what is transfer axis theorem. Okay. So if you need to calculate the moment of second moment of area or the area moment of inertia of a figure about some reference axis, we have an axis AB, then we can use actually a transfer axis theorem. If you know the value of the moment of inertia about the centroidal axis, and if you know the distance between the centroidal axis and the reference axis, we can use transfer axis theorem. So it says that the moment of inertia of a reference axis, which is parallel to the centroidal axis, will be given by the sum of the moment of inertia of the centroidal axis and the product of the area of the figure and the distance between the centroidal axis and the reference axis, that is IAB equal to the sum of the moment of inertia of the reference axis and the product of the area and square of the distance between the reference axis and our centroidal axis. So we need to derive the equation, derive the result. So considering an elemental area dA at a distance y from the centroidal axis. So this is our centroidal axis, this is our centroid, and this is our reference axis AB. So the moment of inertia of AB is denoted by IAB, and the moment of inertia of the central axis is denoted by IG. Okay, so we are considering an elemental area at a distance y from the central axis. So, okay, fine. IAB, according to our definition, IAB equal to the total distance, the square of the integral of the total distance between the elemental area and the reference axis, that is x plus y is our total distance. So r square dA means x plus y, the whole square d. Okay, expand the equation. Fine, we'll get it is in the form of a plus b the whole square. So it is a square plus 2hy plus y square. Right. So now again expand. It is integral x square dA integral 2hy dA plus integral y square dA. Fine, h is a constant there because there is a distance between the reference axis and the centroidal axis. So we can write this one is h into a. The integral of dA is a. So this is x square into a. Fine. Then 2hy dA. So h is a constant, so 2h we can take outside and the integral y dA and integral y square dA. What is integral y square dA? That is actually Ig, the moment of inertia of the centroidal axis, above the centroidal axis. So this term becomes 0. Why this becomes 0 there? Because integral y dA, what is integral y dA? You know the integral y dA is our y bar. So integral y dA become integral y dA become y bar, that is the distance of the centroid from the centroidal axis. That becomes 0 because we know that y is the distance of the elemental area from the centroidal axis and y bar from the centroidal axis is 0. So this term becomes 0. So finally we can rewrite the equation, that is Ig plus ax square, Iab equal to Ig plus ax square. This is the derivation of parallel axis theorem. So we can define the parallel axis theorem like this. The moment of inertia of an axis, moment of inertia of an area about some referral axis which is parallel to the centroidal axis is the sum of the moment of inertia of the centroidal axis plus the product of the area and the square of the distance between the moment of inertia of the referral axis and our centroidal axis. We need to define one more property. It is called radius of gyration. It is denoted by a letter k, small letter k. So I will explain what is the radius of gyration. So okay, consider there is an area A and there is a referral axis AB. So definitely this area has some moment of inertia, the area moment of inertia about this referral axis. So assume that the value is I, that is the area moment of inertia of this area about this referral axis is I. So now we are actually compressing this area into a small strip. So actually these two figures, they are the same area, but in this case the area is actually an irregular figure, but in this case we are actually compressing the area into a small strip and placing this area at a distance k from the referral axis AB. But one condition is there, we have to get the same moment of inertia I in the first case. So we can see that the relative distribution of the area is different in these two cases. In this case it is actually an irregular shape, in this case it is compressed into a small strip and it is placed parallel to the AB. So we need to place the area and in such a way that it would get the same moment of inertia I in the first case. So we need to place this strip at a distance k from the referral axis. So I will be a into k square, like r square dA, I is equal to a into k square. So we can define k is equal to root of I by a. So this is the property. The property of k is called the radius of gyration. Sometimes this question is asked in university question paper, so we need to study this property too. It's called radius of gyration and it is denoted by k. K is equal to root of I by a. Okay, we need to by some results of the moment of inertia of some basic figures like a centroid. We know the centroid of a rectangular, a triangular, and a semicircular, circular sections, and a quadrant circle. Similarly, we need to study the results of this section, the basic section like a rectangular, the moment of inertia for a rectangular area, then the triangular area, circle, and quadrant circle, semicircle, etc. So actually the derivation is excluded from your syllabus, but last time in university they asked a question to calculate the moment of derive the moment of inertia of a rectangular cross section about the centroidal axis. So at least you should study the moment of inertia, the derivation of the moment of inertia of rectangular cross section and a triangular cross section. Actually these are excluded from your syllabus, but last time in university they asked a 3-mark question. So anyway, we need to, at least you need to study the moment of inertia of a rectangular section and a triangular section. So I'm going to derive the moment of inertia of a rectangular cross section about the centroidal axis and about the base AB. So consider a rectangular section of depth D and breadth B. So G is the centroid of this section and XX and YY is the centroidal axis. So we need to, first of all, we need to derive the moment of inertia of this rectangular section about XX. That is, we need to calculate the IGXX. So this is the moment of IGXX is the moment of inertia of the rectangular section about the centroidal x-axis. So for calculating this, consider an elemental strip of thickness dy and which is the distance y from the x-axis. Okay, so the area of the elemental strip is the area of the elemental strip is dA and its thickness is dy, and it is placed at a distance y from the centroidal x-axis. So from the definition you know that the IgXx is equal to integral y square d. So this is the IgXs is integral y square dA. So in this question actually there is the integration limit is, you know that the integration limit is 5. It is d by 2. This is the centroidal axis. This is passing through the distance d by 2 from the bottom. So the limit is minus d by 2 to d by 2. So y is taken in the y direction. Small y is taken in the y direction axis. So the limit is minus d by 2 and then d by 2. So this is okay. Fine. So what is dA? dA is the area of the elemental strip. So dA is actually, it is the breadth b and the thickness dy. So dA is b into dy. So rewrite the equation integral y square into b dy. The limit is minus d by 2 to d by 2. So this is y square into b dy. So breadth is a constant value, so we can take it outside. So finally we can derive this is b into y square integral y square dy. It is y cube by 3 and the limit is minus d by 2 to d by 2. So this becomes v into d by 2 b by 3 taking outside is y cube. It is minus d by 2. Okay. So this becomes b by 3 into dq by 8 plus dq by 8. Okay. So 2 dq by 8, that becomes b dq by 12. So the Igx is equal to the moment of inertia of the given section about the centroidal x-axis is equal to b dq by 12. You need to by heart this equation and you need to know how to derive this equation. So this is the moment of inertia of the rectangle cross section above the centroidal x-axis. Now we need to derive the moment of inertia for rectangular cross section above the centroidal y axis. That is, we need to derive Igy. So for this, consider an elemental rectangular strip of breadth b and depth d. Okay, consider an elemental strip at a distance x from the centroidal y axis and which has a thickness of dx, and the area of the elemental strip is dA. So we know that the definition, from the definition it is Ig by v equal to integral x square dA. And what is dA? dA is the area of the elemental strip, that is the depth d and the thickness dx. So it is d into dx. So this becomes integral x square into d into dx. Okay, d is a constant, we can take it outside, and it is d into integral x square dx. So we know the limit is in this case it is calculating from the x in the y axis. So it is b by 2 minus b by 2 and b by 2. Positive x axis it is b by 2 and negative x axis it is minus b by 2. So this is minus b by 2 to b by 2. Fine. So d into x square dx, integral of x square dx is equal to x cube by 3 minus b by 2 to b by 2. It is d, taking 3 outside, it is, and applying the limit b by 2 the r cube minus b by 2 r cube. This will become d by 3 into b cube by 8 plus b cube by 8. Finally, it is db cube by 12. So the final answer is IGY is db cube by 12. So this is the moment of inertia of the rectangular strip about the centroidal yy axis. Okay, so IGX is equal to BD cube by 12 and IGYY equal to DB cube by 12. Okay, the last part of the question we need to find out the centroidal, the moment of inertia of the rectangular section about the base AB. So for calculating the moment of inertia of the rectangular section about base AB, we are applying our parallel axis theorem or the transfer axis theorem. So what is parallel axis theorem says? Parallel axis says that IAB equal to IG plus AX squared. That is the moment of inertia of a referral axis which is parallel to the centroidal axis is equal to the sum of the moment of inertia of the centroidal axis and the product of the area and the distance between the our centroidal axis and the reference axis. So we know that the moment of inertia of centroidal XX axis, that is IGX. So in this case we can say IAB equal to IGXX plus the product of the area and the square of the distance between the two axes. So if you are considering an axis which is passing through the base AB, so the moment of inertia of that axis equal to IAB is equal to IG, the centroidal sum of the centroidal moment of inertia and the product of the area and the square of the distance between the two axes, that is d by 2 the all square. Okay, we know that area of the strip is B into D and IGXS we have already derived the formula. IGXS is equal to BDQ by 12. So substitute the values is BDQ by 12 plus B into D into D square by 4. So it is BDQ by 12 plus BDQ by 4. So this becomes BDQ, it is okay, it's BDQ by 3. So this is IAB, the moment of inertia of a rectangular section about the base AB is BDQ by 3. Okay, thank you.